Welcome to today's episode. We're diving into the intriguing world of data structures, specifically focusing on Blink trees. These structures have some unique properties that play a crucial role in transaction processing and recovery. We'll see how they enhance concurrent access and maintain data integrity, all while ensuring transactions are executed efficiently. So, let's jump right in. At the core of our discussion are Blink trees, which are a sophisticated extension of B-star trees. Now, you might wonder, what exactly makes Blink trees special? Well, they introduce high keys and sibling link pointers. A high key in a Blink tree represents the maximum key value for any subtree, which makes navigation and searches within the tree much more efficient. Each node, except for the root, contains two pointers. One points to its child node, while the other connects to its sibling at the same level. One standout feature of Blink trees is the half-split state. This state comes into play when a node is referenced by its sibling pointer, but not by the child pointer from its parent. If a search key surpasses the node's high key, suggesting there might be a concurrent modification, the search algorithm can easily follow the sibling link to continue searching without needing to restart the whole process. Now, let's talk about the performance advantages of Blink trees. Their design offers significant benefits, particularly when it comes to speed. By allowing the sibling pointer to be updated quickly while postponing the update of the parent pointer, Blink trees minimize the need to hold a lock on the parent node during descent. This is especially useful during splits, as it allows for concurrent reads and modifications without compromising data integrity. Although this approach might seem slightly less efficient due to the extra page access it requires, it actually simplifies concurrent operations. Since splits are infrequent and B trees typically don't shrink, the performance cost is quite negligible. The upside includes reduced contention, fewer locks held during modifications, and a decrease in the risk of deadlocks that can occur from concurrent changes. Shifting gears, let's look at transaction processing, a vital component of database management systems. The main goal here is twofold. We want to improve efficiency through concurrent transaction execution, while ensuring that these transactions stick to the ACID properties: atomicity, consistency, isolation, and durability. Now, concurrent execution can lead to various anomalies, but we can mitigate these by implementing different isolation levels. So, what are isolation levels? They dictate how transactions interact with one another, ensuring the integrity of data is maintained even when multiple transactions are happening simultaneously. Another crucial aspect of transaction processing is the page cache. This component minimizes disk access by storing frequently accessed pages in memory. When the cache reaches its limit, older pages are flushed back to disk. This mechanism is essential because it ensures that any unflushed changes are preserved in case of a node crash, supporting transaction rollback. To guarantee durability and aid in recovery, we also use write-ahead logs, or WALs. These logs keep track of changes before they are committed to the database. The coordination between the page cache and WAL is managed through force and steal policies, ensuring that transactions can be executed efficiently while maintaining data integrity. As we continue exploring transaction processing, we must understand isolation levels and concurrency control mechanisms. Isolation levels define how transaction operations are visible to one another, which impacts the likelihood of anomalies like dirty reads, non-repeatable reads, and phantom reads. Concurrency control approaches determine how transactions are scheduled and executed, balancing the need for efficiency with the requirement for correctness. By implementing robust concurrency control, systems can allow multiple transactions to operate simultaneously without violating those essential ACID properties. In summary, Blink trees provide a powerful enhancement to B-star trees, facilitating efficient concurrent access and simplifying transaction processing. By leveraging high keys and sibling pointers, these structures minimize contention and deadlocks, allowing for smooth data operations. Coupled with effective transaction processing techniques, including page caching and write-ahead logging, they ensure that databases can handle concurrent transactions while preserving data integrity. Thank you for joining us today as we explored the intricate relationship between data structures and transaction processing. Stay tuned for our next episode, where we'll continue to unravel the complexities of database management systems. Until then, keep exploring and learning.